Okay, let's review what we talk about covalent compounds. And when we are talking about covalent compounds, we are talking about compounds that form molecules, small molecules like water, for example. And we saw how these compounds can be made by the combination of two different atoms. For example, if we have hydrogen and hydrogen, okay, the hydrogen on the left has one electron and needs one. So this hydrogen on the left has one electron. The hydrogen on the right has also one electron and needs one. So they are going to share a pair of electrons. And we saw that this was the dot and cross diagram for the covalent compounds. Yes, like a layer or a Venn diagram where we represent the electrons, and the electrons that are in the intersection of that Venn diagram means that those electrons now do not belong to any of those, but they belong to both together. Yes? So that was the dot and cross diagram. And then we have also the display formula, which is going to show a dash for each pair of electrons. In this case, they are sharing only one, so we are going to have one layer or one dash only. And this is a single covalent bond. Now, we're going to add something else to this one. Why is that? Let's pretend that these are two elements that want that pair of electrons. Who has more power to attract that pair of electrons? This hydrogen or this hydrogen? Or they are the same? They are the same, yes? So when we represent the formula or the molecule of, let me do it in a different way. So if we need to represent the molecule of hydrogen, we can represent it like this. So we have a hydrogen here and a hydrogen here, yes? And the cloud of electrons is going to be evenly distributed around both of them. Why is that? Because they pull that pair of electrons with the same force. That force of pulling the electrons is what we call electronegativity, and we are going to talk about the electronegativity a little bit later, okay? But in this case, what we say is that the molecule is not only single covalent bond, but also is non-polar. Why non-polar? Because we talk about polarity when we have kind of a magnet that has a positive sign and a negative sign. In this case, all the positive signs and the negative signs inside those cloud of electrons are symmetric. The molecule is symmetric, the molecule is non-polar. Yes? You are going to understand this better when we do some more exercises. Yes? This is the display formula. And the molecular formula is what? H2. Good. This is the molecular formula. Yes, that's why we represent the hydrogen as H2. Let's do another one. Okay, and in this case, I'm going to do hydrogen. And can you open the door, please? So you have hydrogen here, and we are going to put a chlorine. Who is bigger, the chlorine or the hydrogen? Chlorine. The chlorine. It makes sense because it has more layers of electrons, yes? So we are going to do a chlorine. Oops. Let me do the undo here. Okay. We are going to put the chlorine that is bigger, okay? And I'm going to take this one and move it a little bit. There you go. Okay, so then we have the hydrogen here, which has only one electron, and the chlorine here that is going to have 1, 2, 3, 4, 5, 6, and 7. Is that okay? Now, there is something here that is different. Do you think that the hydrogen is going to have the same force as the chlorine to attract those electrons? No. Actually, the chlorine is more what we call electronegative. Okay? So if we draw the molecule, I'm going to do it without those shapes because it's a weird shape. We are going to have a small part for the hydrogen and a bigger part for the chlorine. Why is that? Because because we said the chlorine is more electronegative. That means that the chlorine is going to spend more time with the electrons around it than the hydrogen. Yes? Now, that makes the chlorine and the hydrogen all together forming the hydrogen chloride a polar molecule. Why is that? Because if you think this as a magnet, if the electrons are spending more time around the chlorine, this is going to resemble what we call a magnet with a negative charge here and a positive charge here. That's why we'll call this one a covalent bond. How many pairs of electrons are shared in this case? How many pairs? One, of course, one. So a single covalent bond. Yes, but instead of being non-polar with as the other one, it's going to be a polar bond. Yes?
Yes.
So we have single covalent polar bond. How do you represent the display formula for hydrogen chloride?
Yes, H that with
One line, one dash. Yes, because this dash represents, this dash here represents this pair of electrons. If we have two pairs of electrons, it's going to be two dashes. Yes? And what about the molecular formula? HCl, very good. HCl. Good? So far, so good? Now, we are going to do the last one, and we saw the other day that in the particular case of water, we do not have a linear molecule, we have a bent molecule, yes? So we are going to do the oxygen, and I'm going to do here a hydrogen, and I'm going to do another hydrogen. So we have hydrogen, hydrogen.
So what is water again? Like the scientific name?
Dihydrogen monoxide, but we don't use that. Okay, so this is going to be one dot for every hydrogen, and then crosses for the oxygen. 1, 2, 3, 4, 5, and 6. So we are going to have the molecule of water like this. Since it's not linear, linear would be if it's like this. And last class we saw that that cannot be possible. Okay, so we are going to have a molecule that has how many polar bonds? Look at these, guys. Here I have a polar bond, yes?